Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell. You'll get notifications for this series and a bunch of others on our channel. We're doing Linear Algebra 1. This is Chapter 1, Systems of Linear Equations. 1.7 is Gaussian Elimination and row echelon form. We talked about a little bit more than that. Also, we did reduced row echelon form as well in the last video. But now, in this lecture specifically, what we're going to do is solve some linear n by n systems using Gaussian elimination to row echelon form. Then we're going to use the last row to decide whether we have one solution, no solution, or infinitely many solutions. And then we'll talk quickly about rank of a system and the Kronecker-Capelli Theorem. Let's do that. All right, this is Willa. She came to see what we're doing. We're solving linear systems. There you go. Yeah, very nice. That is a system. We're going to augment the matrix. We're going to use Gaussian elimination to row echelon form. Then we're going to use the last row to see whether we have one solution, no solution, or infinitely many solutions. You ready? Okay. Let's do it. Solve the linear 3x3 system. I have 3 equations and 3 unknowns. How do we solve this? Basically, we immediately augment the system into an augmented matrix, then use Gaussian elimination using those 3 row operations to reduce. I just explained it to the kid that you saw. Let's do it. Augmenting the matrix, I get 3, -2, 6 equals 4, -1, 2, -1 equals 1, and 4, -4, 7 equals 3. This is the matrix. What we're now going to do is, I'll go slow at first, but I want a leading 1 in the top left corner, so we're going to interchange rows 1 and 2. Then I'm going to multiply by a negative to get a positive 1. Therefore, first what we're going to do is interchange rows 1 and 2. Doing that, I get -1, 2, -1, 1, 3, -2, 6, 4, 4, -4, 7, 3. Now what I'm going to do is row 1 goes to negative row 1, or -1 times row 1, and that's going to give me quickly 1, -2, 1, -1, and then the rest is the same. You can slow that down and pause, but basically what I want is the first mantra is get a 1 in the top left corner is what we want to train as a mantra. It'll become Pavlovian. Then what are we going to do? Then you know what move to make. We're going to want to eliminate the x1 variable from this equation and this equation. To do that, well, technically it was this one, but because we made that one then -x1. But once we eliminate those 2 variables from those 2 equations, we can consider the 2x2 system and keep solving that way. So those have to become zeros. With this a 1, it makes the next moves really easy. I'm going to multiply by -3 and add it to this row. And then I'm going to multiply this row by -4 and add it to this row. In notation, that says row 2 is going to go to row 2 minus 3 row 1. And row 3 is going to go to row 3 minus 4 row 1. Once we do that, that will give us the matrix 1, -2, 1, -1. Then what I'm doing is multiplying by -3, distributing it onto every single one, and then adding it to this entry. So 3 minus 3 is 0. That's why we did it. Now we have to turn our brain on to do the rest. -2 plus 6 is 4. 6 minus 3 is 3. And 4 plus 3 is 7. And then now what we're going to do is we're going to multiply this row by -4 and add it to this one. 4 minus 4 is 0. That's why we did it. Now, Thinky Brain says 4 minus 8 or plus 8 is 4. 7 minus 4 is 3. Ooh, it's either a contradiction or infinitely many solutions. What do we get? 3 plus 4 is 7. We get infinitely many solutions. I can tell until you're a wizard. You can't tell until you're in row echelon form. Are we in row echelon form? No, because these guys are lined up. Therefore, what am I going to do? First, I'm going to do row 3 gets replaced by row 3 minus row 2. And we get 1, -2, 1, -1, 0, 4, 3, 7, 0, 0, 0, 0. If you want, we can do one more row operation and get this a leading 1, which I like. But either way, we're going to solve now for our equations. What does this say? In this equation, remember this is a simpler system after we augment. What that means is you can write those equations out again. This is x1 minus 2x2 plus x3 equals -1. And this equation is 4x2 plus 3x3 equals 7. From this equation, which is this guy in this avatar, in the augmented matrix avatar, we can now solve. X3 is free. And we have to solve for x2 and x1 in terms of those guys. From this equation, this immediately says 4x2 equals 7 minus 3x3, which is t, or x2 is 7 over 4 minus 3 over 4t. Then in the last equation, that's going to say, this one says x1 is -1 plus 2x2 plus x3, or sorry, bringing it over minus x3, which gives me -1 plus 2 times x2 is 7 over 4 minus 3 over 4t minus t. So that gives me -1 plus 14 over, or let's cancel that. Let's get rid of that 2. I can make that a 2. So that will give me -1 plus 7 over 2 minus 3 over 2t minus t, which is equal to, what am I going to get? This is 2 over 2, and this is going to be 2 over 2. So I'm going to get 5 over 2 minus 5 over 2t is x1. Now I have all three dependent on one free variable. This is the infinitely many solutions. So in REF, I can tell I have infinitely many solutions. I had a row of zeros, which means I'll get one free parameter. Let's write that nicely in the general solution. The general solution is therefore equal to x1, x2, x3 equals. x3 was t, x2 was 7 over 4 minus 3 over 4t, and x1 was 5 over 2 minus 5 over 2t. There's the general solution, which is infinitely many, which I obtained by augmenting the matrix using the 3 row operations to REF, which is called Gaussian elimination. And then I decide in the last row, once I'm in REF, whether I have one solution, infinitely many solutions, or no solution. Let's do another one. All right, example 2, solve the linear 3x3 system. This time we have this linear 3x3 system where we have some big numbers. What do? I augment the matrix, and I notice this is a 1. So copying this out, putting this row at the top, so I get a leading 1. I'm interchanging rows 1 and 3, or row 1 and row 3 is what I'm doing, and then augmenting. This gives me 1, 2, 3, 26, 2, 3, 1, 34, and 3, 2, 1, 39. Once I augment the matrix, now you can see I have a leading 1 in the top left corner, and I want to eliminate the variables below that. First of all, we're going to do row 2 goes to row 2 minus 2 row 1, and row 3 is going to go to row 3 minus 3 row 1. That will give me a new augmented matrix, which is going to equal 1, 2, 3, 26. That won't change when we go to REF now. Once I have a leading 1, this won't change anymore. Then what am I going to do? I'm going to multiply by -2, distribute it into all of these, and then add it to this one. So 2 minus 2 is 0. 3 minus 4 is -1. 1 minus 6 is -5. And then here, what are we going to get? We're going to get -52 plus 34, which is -18. Here, what am I going to get? I'm going to get, now we're going to multiply by -3. 3 minus 3 is 0. That's why we did it. 2 minus 6 is -4. 1 minus 9 is -8. And in the last spot, we're going to get -3 times 26 plus 39. So 26 times negative 3 is going to give me negative 78, plus 39 is going to give me negative 39. All right, so if you have to do a side calculation, there we go. Now what do I want to do? I want a leading 1. I can cheat by just making this positive, 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 or first what we're going to do is row 2 goes to negative row 2, I guess. Then what we're going to get is 1, 2, 3, 26, 0, 1, 5, negative 18, 0, negative 4, negative 8, negative 39. Now what we're going to do is row 3 is going to go to row 3 plus 4, row 2. That's going to give us 1, 2, 3, 26, 0, 1, 5. That should be a positive 18, 18. And then we're multiplying this one by 4. So negative 4 plus 4 is 0. Negative 8 plus 20 is 12. And negative 39 plus 4 times 18, 18, 40, 72, 39, 33. And then I want leading 1. So I'm going to do, in my last step, I'm going to do row 3 goes to row 3 times 1/12, which is going to give me the matrix 1, 2, 3, 26, 0, 1, 5, 18, 0, 0, 1, 33 over 12. They both have a 3 in them, so 11 over 4 is what we get. This is now an REF, row echelon form. In row echelon form, if the number of variables I had to start off with 1, 2, 3 unknown variables, if I get 3 leading entries, specifically I have leading 1s in row echelon form, then I have a unique solution. Specifically what this says immediately is that x3 is already 11 over 4. I have that one. Equation 2 says x2 plus 5x3 equals 18. So that says x2 is equal to 18 minus 5 times 11 over 4, which is going to be 18 times 4 over 4 minus 55 over 4, which is going to be 17, over 4 is x2. x1 is equal to 26 times 4 over 4, I'm going to guess, minus 2 times 17 over 4 minus 3 times 11 over 4, which is 104 minus 34 minus 33 over 4, which is 37 over 4, which is x1. We now have the unique solution. If we put that in our nice general form, that says that the general solution is x1, x2, x3 equals, x3 was 11 over 4, x2 was 17 over 4, and x1 was 37 over 4. Let's do that one more time at least. I have this system. I augment the matrix. That gives me 2, negative 4, 1, negative 1, 3, negative 1, 2, 0, negative 1 equals 3, 1, negative 1. This is my system. I have a 1 right there. Let's interchange rows 1 and 3. That is going to immediately give me 1, negative 1, negative 1, negative 1, negative 4, 3, 0, 1, and 2, negative 1, 2, 3. Now what we're going to do is we have, where's my other color? I have a leading 1 in the top left corner. I want to eliminate below. How do we do that? We are going to do row 2 goes to row 2 plus 4, row 1. And row 3 is going to go to row 3 minus 3, row 1. Multiplying by 4, first of all, what do I get? I'm going to get 1 minus 1 minus 1 minus 1. This is negative 4 plus 4 is 0. 3 plus negative 4 is negative 1. 0 plus negative 4 is negative 4. 1 minus 4 is negative 3. then what we're going to do is multiply by negative 2. 2 minus 2 is 0. 1 plus 2 is positive 1. 2 plus 2 is 4. And 3 plus 2 is 5. Then what we're going to do is, let's add those two rows together. So row 3 goes to row 3 plus row 2. That gives me 1 minus 1 minus 1 minus 1. 0 minus 1 minus 4 minus 3. And then what am I going to get? 0 plus 0 is 0. 1 plus minus 1 is 0. 4 plus negative 4 is 0. 5 plus negative 3 is 2. Technically, I just want to multiply and get rid of that negative, so I cheated. Or let's not cheat. What have I done? Row 2 goes to negative row 2. And that's going to give me 1 minus 1 minus 1 minus 1. 0, 1, 4, 3, 0, 0, 0, 2. This is bad. What that says technically is 0 equals 0 times x1 plus 0 times x2 plus 0 times x3. But this is saying that equals 2, or 0 equals 2. This is a contradiction, and we have no solutions. Let's do another one. All right, example 4. Solve the linear 2 by 3 system. We're given two equations in 3 unknowns. This is the hundredths fallow problem. Basically what it's saying is we want 3 kinds of birds, roosters and hens and chicks, and we want 100 of them, and we only have $100 to spend, and we know that roosters worth $5, a hen is worth $3, and 3 chicks are worth $1, or each chick is worth 1/3 of $1. This is the system we get. Let's solve this system and find all of the positive real-world solutions to this. In the original problem that was listed 2,500 years ago, he lists 3 positive solutions. And if we know anything about our linear systems, there's only ever one infinitely many or no solution. Since he lists 3, it can't be 1 or none, so there has to be infinitely many. Then we'll find all of the positive and in fact non-zero solutions to that. Augmenting the matrix, I immediately get 1, 1, 1, 100, 5, 3, 1/3, 100. What I'm going to do is multiply by negative 5, so row 2 is going to go to row 2 minus 5 row 1. And that will give me 1, 1, 1, 100. And we're going to get 5 minus 5 is 0. 3 minus 5 is negative 2. And 1/3 minus 5, negative 3 over 3 is going to be negative 14 over 3. And then 100 minus 500 is negative 400. Once I have that, I'm going to do row 1, or row 2 goes to negative 1/2 row 2. And that will give me the matrix 1, 1, 1, 100, 0, 1, 7 over 3, 200. And what that tells me is this is now REF. If I have leading ones, is there any 0 rows? Technically there is one, but it was never there. It was never given. So they're below any non-zero rows. If we have leading entries, there's 0 below where we can have this. And in any 2 rows that I compare, which I only have 2, this one is further to the right than the upper row. Therefore, I'm in REF. What does this tell me? I have infinitely many solutions. And this says that x2 is equal to 200 minus 7 over 3t. x3 is equal to the free parameter t, and x1 is equal to 100 minus x2 minus x3, which is 100 minus 200 minus 7 over 3t minus x3, which is t. So x1 is equal to negative 100 plus, I have 7 over 3t minus 3 over 3t, so 4 over 3t. What that tells me is my general solution, there's infinitely many solutions, and my general solution is x1, x2, x3 equals, equals, equals. x3 was the free parameter, x2 was 200 minus 7 over 3t, and x1 was negative 100 plus 4 over 3t. This is my general solution. But now we have one more added problem. We want to find the positive solutions because there can't be fractions, first of all, of birds, and then we can't have negative birds, so we want the positive integer solutions to this, or the Diophantine solutions to this linear 2 by 3 system. What are those? Specifically from these, if we make a shift, we could make t equal to t tilde to equal 3t tilde. Long story short, when I substitute that substitution in there, I can get, or refudge it that way, if I let this equal 3t and then t, that should be negative 7 over 3. So, sorry. That should be plus 4t and minus 7t, and this will be 3t. Once I have that, that will help me find the integer solutions easier this way. Therefore, now we're going to have no more fractions, so we'll have whole solutions by making that fudging factor of the parameter. And then what we can do is to find all the positive solutions. We have two conditions here. What we need is x1, which is negative 100 plus 4t, has to be greater than or equal to 0. And x2, which is 200 minus 7t, has to be greater than or equal to 0. This inequality gives me immediately that 4t is greater than or equal to 100, or t is greater than or equal to 25. And this one says that 200 is greater than or equal to 7t, so 200 over 7 is greater than or equal to t. Who is this guy? This is 7, 200. 7 goes into there 2 times. I get 14. I'm going to get 60. 60 is going to be 8, which is 56, and I'm going to get plus 4. And so that says that this is going to be t is less than or equal to 28 and 4/7. So that gives me bounds, essentially. Long story short, yeah, solving real world problems is harder. Solving the linear system here, you're done if I ask you, but if it asks for the positive real world solutions for the interpretation, we have to now do this. What that told me is, cleaning this up, what are my two inequalities? T is larger than 25. So we have 25 is less than or equal to t is less than or equal to 28 and 4 over 7. Therefore, we have 25, 26, 27, 28 are the possibilities for t that we can try, and those, in fact, are the 4 non-zero solutions that we get. We get the ordered pairs 0, 25, 75. This is when t equals 25, t equals 26, t equals 27, t equals 28. Here, we're going to get 4, 18, 78. Here, we're going to get 8, 11, I believe, and 81. I had to cheat. I'm not going to put all the values in. You don't need to see me do this. Calculate on the side. And then this one is going to be 12, 7, 84. Did I get those all right? Yes. No. This should be 4. Subtract 7 from each one. Long story short, these are the combinations of, remember, rooster, hen, and chicks that we could possibly buy. In the original paper that was 2,500 years old, they listed these 3 positive solutions, but now you can see, long story short, there's infinitely many solutions. There's 4 positive solutions, and there's 1 non-negative solution where you could buy no roosters and just hens and chicks, but then the next year you don't have anybody to make more roosters and chicks and hens, so you got to go back to the market. Let's talk about rank and the Kronecker-Capelli theorem. What we know. Okay, to end off this video, the definition of rank of an augmented matrix is the number of leading entries and therefore the number of non-zero rows in row echelon form. This is denoted by rank AB for the augmented matrix, and similarly the rank of the coefficient matrix, just A, is denoted by rank A. What the Kronecker-Capelli theorem tells us is, given any linear m by n system S is consistent, which means it has at least one solution, which means, therefore, by our previous theorem in the last video, we have either one solution or infinitely many solutions, if and only if we have that the rank of the augmented matrix is equal to the rank of the coefficient matrix. Let's look quickly at one example of what that actually means, because this notation, I know you just stare and nod and you're not quite sure what that means. So here's a baby example on what they mean by this theorem, and it gives you a quick check on whether the system is inconsistent. All right, as a baby example, we do the one x1 plus or x plus y equals 4 and x plus y equals 3. This is inconsistent. We already know this. We've done this in a previous video. You can go watch. There are no solutions, but let's augment the matrix. That gives me 1, 1, 4, 1, 1, 3. This is the augmented matrix. And the coefficient matrix is 1, 1, 4, 1, 1, or sorry, just without the column. This is the coefficient matrix A. When we row reduce, what that says is row reducing, this will give us 1, 1, 4 we saw, and 0, 0, negative 1. But if we row reduce this without the column, we're going to get 0 and 0. So this is our REF here, and this is versus the REF of A, which is 1, 1, 0, 0. Now at first, this is a lot of moving parts, but what's the rank now? The rank is the number of non-zero rows in the augmented matrix. So we have 1, 2 non-zero rows. So the rank of this is 2. But the rank of this is we only have 1 non-zero row here. So the rank of this is 1. So the rank of A is 1, which does not equal 2, which is the rank of A equals B. So that says no solutions. It's inconsistent because the rank doesn't match. Any consistent system, you will always have that the rank of the augmented matrix equals the rank of the coefficient matrix. Please subscribe right here, hit the notification bell. I'll see you next time.